glad you made it out on this kind of unseasonable for San Antonio night. My name is Fred Loxam. I'm Associate Vice President for Academic Affairs, and it's my pleasure to invite you, to welcome you to the first Distinguished Science Lecture Series. If you're looking in the background, you can see there are two other talks in this series, one in December, then one in March. And I welcome you to come back, and I hope that you do. The way this will work, after a couple of introductions, Professor Zare will give a very interesting talk. And you're welcome to, afterward, to use these microphones to ask questions. So that'll be an opportunity afterwards. I wanted to just mention a couple of things about the Distinguished Science Lecture Series. It's funded by a gift from the Walter F. Brown family, as indicated on one of the slides. And we're very grateful to the family for making that gift, making this lecture series possible. And the way a visit works, you might think that Professor Zare will just give the speech tonight, but in fact, we like to put that Walter F. Brown family money to work by putting the speakers to work. So he'll do three kinds of things during his visit, which I think is pretty wonderful. It's the kind of place that Trinity is. First, there's this interaction with the San Antonio community, with you as a way of bringing his very interesting science to a wide group of people. He will also have high-level, important, interesting discussions with faculty in the chemistry department and in the molecular biology and biochemistry group. So he'll work with faculty. And I would say, most important, he'll be meeting with students. So tomorrow he'll give a seminar for faculty and students in the chemistry department. He'll go to lunch with students. So this is really important because that's what Trinity is. We're about all of these things, interacting with the community, doing research, and also, most importantly, working with students and nurturing students. Now, one of these fine students will introduce Dr. Zare. She's Camille Potts, and she's on the stage here. That's Camille. She's a junior. She's from Houston. Yay, Astros, right? Yeah. She's a biochemistry and molecular biology major, and she does research with Karina Mader, who's here, her advisor is here, on pre-messenger RNA splicing, and she plans to attend graduate school. And now she plans to introduce the speaker.
Can everyone hear me okay? From the back? Yeah, thumbs up, thank you. So hello, we're here today to watch a talk by Dr. Richard Neil Zare. Dr. Richard Neil Zare is the Marguerite Blake Wilbur Professor in Natural Science and a Professor of Chemistry at Stanford University. His interest in science began when he was a young child and led to him setting his basement on fire while experimenting with chemicals he had purchased from a local pharmacist. As an undergraduate, he majored in chemistry and physics at Harvard University. Dr. Zare began to pursue his PhD at the University of California at Berkeley and finished his degree at Harvard. After a brief postdoc at the Joint Institute for Laboratory Astrophysics at the University of Colorado at Boulder, Dr. Zare worked at MIT, then again at the University of Colorado, then Columbia University, before finally settling at Stanford University in 1977. Throughout his career, Dr. Zare has worked in the intersection of physical and analytical chemistry, most notably in contributions using laser chemistry to understand chemical reactions at the molecular level. He is well known and respected for his development of laser-induced fluorescence as a method for studying reaction dynamics. Notably, his research has stretched beyond conventional lines between fields. Dr. Zare's work spans from collaborations with NASA on Martian meteorites all the way to analyzing bubbles in beer. Just to show his remarkable amount of contributions, let me tell you, Dr. Zare has authored or co-authored more than 800 publications, written 4 books, holds 50 patents, and has been actively involved in national science policy. Among many other accolades, Dr. Zare has been elected to the National Academy of Sciences and has received the Priestley Medal, which is the highest honor from the American Chemical Society. Dr. Zare has also been recognized for his contributions to teaching. Dr. Zare's passion for teaching and mentoring led to him being named a Howard Hughes Medical Institute professor. Dr. Zare has mentored over 150 PhD students and postdoctoral researchers, many of whom have been women and members of minorities. Dr. Zare is known for his strong advocacy of women in science, including his work to establish maternity leave within the Stanford chemistry department, a move which prompted Stanford to adopt a university-wide policy of maternity leave. He has also spoken up for using Title IX to advance gender equity far beyond university athletics. We're very excited to have Dr. Zare and his famous enthusiasm for science at Trinity University tonight. Please welcome Dr. Zare.
What a pleasure to be here, to return once again to Trinity. I have not been here for about 20 years, and I cannot recognize the transformation, amazing transformation that's taken place on your campus, and all very much for the good from what I can see. It's a pleasure to be with you. I want to start on a topic that is very seldom discussed, from what I can tell. This is a topic of, well, let's see, I'll have to do this by switching off this moment. See if I can do this. Escape. Okay. And then we'll do like this. This we don't need. Okay, and we'll go back here. And then we'll put this away. And then we'll go from the slideshow, we'll go from the beginning. This ought to do it, I hope. Is that working? Yes, great. Okay, so let's now begin with this lecture, and it is going to be on human alcoholysis. What is alcoholysis? It is the metabolism of humans of alcohol, and this is common in lots of places. Very few cultures are without alcohol. I think one major exception has been the Eskimo, because it's just too cold to actually get fermentation to happen, which is the beginning, okay? But otherwise, it's all over, and we can trace all types of things that have started, such as, for example, beer starting, I think, in Egypt with mead and stuff like this. But we're gonna begin, and the topic I want to discuss. Oh, better say this to you. I'm at Stanford, but important thing is that's my email address. None of you need to take any notes. Sometimes taking notes is good and helps you learn things, but if you email me at this address, I will send you this PowerPoint presentation. Okay? So if you want it. And you have it. So I think you might find it worth studying, some of you. Let's begin. The question I want to ask is, how fast and how long does the consumption of alcohol affect human activity? That's the topic that we're going to look at. A fair question, I think. And I'm telling you, it's all a matter of chemical kinetics, how fast chemical reactions occur. And so I'm now going to actually dive into chemical kinetics, keeping in mind our goal is to understand an answer to this question I've asked. So we're going to look first at chemical kinetics. And so here we go, kinetics. Chemical reactions can be what? They can be slow. An example is tarnishing of silver, right? Or they can be medium, and the answer is blood clotting. Very important. It's not too fast and not too slow. Think about it, right? Or it can be fast, and the best example of a fast chemical reaction is an explosion, right? And firecrackers to other things. Okay, fine, we have that. And we're going to talk about the reaction rate, how fast that happens, as the rate at which the concentration of one of the starting materials called reactants or ending materials called products changes in time. We want to know the rate at which they change in time, their concentration. Okay? How their amount goes in time. And this automatically leads us to try to look at this in a very general way and talk about what this means. Suppose we have some generic reaction, I don't know what it is, A plus B plus whatever else goes on to M plus N plus and so on, right? Now, let's define the rate. And the rate is going to be, in the case of a reactant, it is how fast it disappeared. And that's the derivative, dA dt. That's brackets around that, square brackets to indicate it's a concentration. Okay? So that's the concentration of A that disappeared over a small time interval. If you'd like deltas instead of D, but you get the idea of what derivatives are, and happily many of you have had this. Okay, you have a feeling for this. Okay, that's what the rate is. And what else? It's also equal to the rate at which a product appears. It's the concentration of M that appeared over the small time interval. That's what we mean by rate. Okay, we're going to use that. And let's now talk about the general form of a reaction rate law. This arbitrary reaction has a rate given by some constant in front of it, and then the concentration of A raised to some power, like the M, and B raised to the nth power. These are exponents. And they're often integers. They don't have to be integers, but they often are integers. And I want to go over this with you. So here's the K, the rate constant, which in general it's temperature dependent. Okay, and M and N may also be 0. This is in the beginning, at least it was to me, a big surprise. Well, how can you get 0? What do you mean it doesn't depend? 0, and something raised to the 0th power is 1. So nothing happens, right? Why is it that it doesn't matter about the concentration of some species in a chemical reaction? It doesn't seem to have anything to do with making a balanced chemical reaction at all. Okay, let's go on. So here's an example for M equals 0, N equals 2. We would have the rate as K, A to the 0, B squared, or just KB squared, right? That would be, and we would say it's 0th order in A and 2nd order in B. Giving the order being what is the exponent. Okay, but how could this come about? What's going on? So I want to give you an example, if I might. Let's consider a group of 3 students, okay, that are going to assemble a magazine, a school magazine, okay? And the magazine was going to have 50 pages, and the pages have been printed and stacked in piles, 1 pile for each page. So imagine there are 50 piles of paper on this floor. Okay, now, right? And what do we have? Student X assembles the pages in order, picks up page 1, puts it in the front, puts page 2 in back of page 1, keeps walking and putting the magazine together, right? That's what X does. Student Y straightens the pages, and student Z staples them, puts a staple through them. Think what happens. Student X can assemble 20 magazines an hour. Y can straighten 120 per hour, and Z can staple 200 per hour. What's happening in this situation? Everybody's waiting for student X to pick up those 50 pages and hand it off to Y, who straightens them and gives it to Z, who puts staples through them, right? Okay? The first step in this process is what we call the bottleneck step. This term bottleneck comes from milk bottles. How fast can milk pour out of a bottle? No faster than depending upon the neck of the bottle, how big it is. That's the bottleneck in the process. Okay? That's the idea where that comes from. So almost as soon as a magazine is assembled, it is straightened and stapled. We cannot speed up the rate of magazine production by assigning more people to straighten or staple. Doesn't work. Get 3 more people to straighten and staple, worthless. Get more people to pick up the assembly, we get something. In other words, it's 0th order. Doesn't depend on the concentration, the numbers of people who straighten and staple. It really depends on the number who can pick up and assemble the magazine. So we get an idea now of something that how it goes in kinetics. This is common. I don't know how many times I've seen a number of people who are doing work. And it is often the case that one person is working and several people are standing around watching the person who's working. This is very common. It comes from certain bottleneck events. It's what they're waiting for. Okay, so the conclusion, it's simple. The rate depends only on the number of students assembling the magazine, which is the slowest step in the process. This slowest step has a number of names: the bottleneck step, the rate determining step, the rate limiting step, the rate controlling step. They all mean the same thing. Okay, you'll see people talk about this. And now I'm going to go and try to put this into more mathematical terms. There's a feeling some have expressed to me, even today, that for some things you just don't need any math at all. Okay? Well, yeah, sometimes you can find things you don't seem to need any math at all, but having some mathematical ability can really sharpen what you're able to do, and we're going to see that here very much. So let's look at these integrated rate laws. Here is a 0th order elementary reaction. A goes on to form B plus C. Okay? We'll be more specific about this later, but right now let's get the idea across. So that means minus dA dt is whatever that K is, K naught, A to the 0th power. Well, that's just K naught. This means that dA is minus K naught dt. I've just moved things to different sides of the equation, right? And I can integrate that, right? From the starting concentration, A naught, to whatever it is at time t. And when I do that integration, well, that's simple. That's AT minus A naught, right, is minus K naught t. Or solving just for AT alone, it is the original concentration, and look at it, it's falling off with time, linearly with time, just as a function of time to the 1st power. That's what I mean by linear with time. That's a 0th order process. And we now see it's actually quite possible to have things that operate at 0th order. Okay, good. Let's go on, and we'll do the next step. Well, we'll do 1st order. This is all just math, right? And for some of you, I mean, I know you haven't seen it. For others, and that's okay, because we're telling you the result. I am, anyways. Others of you have had some familiarity with this, and you'll see this in action in a little bit. Okay, so let's go. That's going to be minus dA dt is K1, now A to the power 1, or just A. Well, I'm moving this to this side of the equation. To this side of the equation, I have dA over A is equal to minus K1 dt. And I'm going to integrate that. And you might recognize this as being the derivative of the logarithm, the natural logarithm. Okay? And so when I integrate this goes from the natural log of A at t minus A at 0. And this integral is very easy. That's just K1t, okay, with a minus sign. Good. And this means I can put these together like so. Remember, log of something minus the log of something else is the log of the one thing divided by the other, right? Okay, and that's K1t. And now I want to get rid of that natural log. And how do I get rid of a natural log? I exponentiate both sides of the equation, right? Make it an exponential power. And in doing that, I get AT over A naught is equal to exponential of minus K1t. And solving for A of t, great formula, right? We see that A of t, the concentration of A at time t, is related to the initial concentration, A naught, and it falls off exponentially with time with this constant K1. That's how fast it's falling off. This 1st order kinetics is exactly the kinetics of, for example, radioactive decay, how fast things disappear as a function of time. And people have used that, for example, for dating, various things that you know about. Okay, and many other uses of it. Okay, fine. So we have that feeling for how this goes. Now we want to go on and define what's called a half-life. That's the time it takes the concentration to reduce to half its initial value. That's called a half-life. So what's the half-life of this process, people ask? Well, let's look it out. Let's work it out. Denote the half-life by T subscript 1/2. That'll be the half-life, okay? And that means this thing, we know where that comes from. Now, at the half-life, when T is T 1/2, then we have 1/2 A naught over A naught. These cancel. We have the logarithm of 1 over 2, which is the log of 1 minus the log of 2. Log of 1 is 0, right? So that's just minus log of 2. And then solving that, we see very much that the half-life is just given by the natural log of 2 over K1, or 0.693 over K1. So all this is known. That's where it all comes from, okay? And so we can relate half-lives to this constant K1. Now, let's go on to alcohol. By alcohol, I'm referring to ethanol. What's that? CH3, CH2OH, right? Okay. And, okay, so what do we have? We have different pathways, but the most important pathway is there's an enzyme in our liver called alcohol dehydrogenase, or ADH. And alcohol dehydrogenase takes this ethanol and it turns it into what's called, pointer's pretty tired, acetaldehyde. I'm going to see if I have a better pointer in my briefcase. Let's try this one. That's working, good. Now, I have to have this too. Okay, so it's turned ethanol into acetaldehyde. Okay, and this aldehyde, there's another thing called aldehyde dehydrogenase, and it takes the aldehyde into acetic acid or acetate. That's the stuff that you find in vinegar. Okay? And your body, if you have these enzymes, okay, goes through these steps. And what happens to the vinegar, the acetic acid? You urinate it. You piss it away, okay? Those of you who drank a lot of beer understand exactly what I'm telling you, okay, what's going to happen in this. Okay, and this is how it is. Now, not everybody has the same amount of enzyme. And in particular, now this becomes genetics as to what enzymes you have. There are some groups of people who are missing the aldehyde dehydrogenase. It's nearly absent. And so the result is that acetaldehyde accumulates in them. Not good. Okay? They don't like it. It doesn't feel good at all. They tend to get very red in the face and they don't enjoy drinking, okay, at all. Now, you may have noticed some people or know such people, just for fun. People who've seen this? A whole bunch have, right? And there are various groups that are this way. And we don't need to say more, but that's what's going on, okay? So we understand that. Well, let me try to get this to work. We're going to go about viva la difference, okay? Differences in alcohol metabolism. Let's go through this. Men and women are not the same. They have different responses to alcohol. For women, blood alcohol level rises faster. Thus, women become intoxicated more quickly than men with an equivalent dose. In addition, women metabolize alcohol at a slower rate than men. And there are other factors that account for the greater effect that alcohol has on women than on men. One of them is body size. Depends on your body size, as we'll go over this. And the smaller your body, the more, with the same amount of alcohol, obviously you're going to have a higher alcohol concentration in you, which is why it's so much more powerful on children than it is on adults, okay? Body composition. Women have less water to dilute the alcohol since they have a higher percentage of fat than men, okay? Less enzyme activity and so forth. We're getting an idea. Incidentally, rather amazing, the law, which is involved in this, makes no distinction between men and women. But in many states, we'll go into what Texas is like later, but very interesting. Okay, but this is the real reality. But now we need a model for how alcohol works. I'm grateful to my own advisor, Professor Dudley Hirschbach, who showed me this very simple model. Now, this is really a model. It's a simplification. Life in us is much more complicated. There's different variations in enzymes. I mean, it's much, much more complicated. But there's a nice model which captures within about 10% all that's happening. And that's what I want to talk about tonight. A very simple model. Let's go through it. And it's a two-step process. A goes to B, and then B goes on to C. Right? Two-step. And what is it? What are we talking about? Step one, the transfer of alcohol in stomach and upper intestine to aqueous fluids in the body, such as blood, and it turns out to be first order with a rate constant K1. And the half-life of alcohol in the bloodstream is about 4 minutes for most people, and the typical volume of aqueous fluid in a person is about 40 liters. Depends on your size, but that's about 40 liters. And thus, if you work this out, K1 turns out to be this value per minute, or 0.173 per minute. That's K1, okay? Great. That's K1. We have now the idea of what's happening. First order from into our blood, and how it's disappearing from our blood. Okay, now what's it going to? In the liver, an enzyme that I've mentioned to you before called alcohol dehydrogenase converts ethyl alcohol to acetaldehyde with a 0th order rate constant, K0, whose value is about 0.17 moles per hour, or divided by 60, you can put it in moles per minute. And that's what it is. That's its nature. Okay, and that's in our liver, that we have that. Now, it's interesting, this process of converting an alcohol to an aldehyde and then to the acid works for other alcohols. And some of you remember the molecule methanol, CH3OH, not ethanol, but methanol, wood alcohol. Why is wood alcohol so bad for you? That's what I want to get to. Well, the same enzyme takes it and turns it into formaldehyde. That's the next step. And goes on from formaldehyde, worse still, to form formic acid. Formaldehyde is what people embalm bodies with, okay? Formaldehyde is very reactive with proteins, what's called the Schiff-base reaction, links them together. People first go blind in their eyes with wood alcohol, and then it gets worse. What's formic acid? Formic acid is what you find in bee and wasp stings, right? You don't want formic acid in you. Okay, acetic acid, vinegar, I can deal with. Formic acid, no. So wood alcohol is very bad, okay? And we'll talk about that. And we can talk about other things and what they do the same way. Okay, we'll move on. So now we got K0. And K0, I'm telling you, is a 0th order process. This enzyme works at 0th order. For those of you who've had courses about this, and remember something called Michaelis-Menten kinetics, this is in the limit where all the sites get saturated, which is quickly what happens. It's running 0th order. And this is the nature. Okay, fine. Okay, we understand this. Now, let's put it all together. So we have this two-step process, and we even know K1 and K0. So here we go. Here is dA dt is K1A, and we know how to solve that. And dB dt, okay, what happens? It is being formed at the rate of K1A, right? And it's being lost at the rate of minus K0. It's a zeroth order process, okay? And I'm going to substitute for this A, this expression here, that's dB dt, and then guess what? I'm going to integrate this. And again, no point, I don't get anything out of people who do math in front of me. For me. Some other people may, I don't, okay? You got to do it for yourself. That's what I find. And I'm doing it here, and this is the answer. And we go through the integration, and here it is. And it says that the concentration in B, okay, that's our alcohol in the bloodstream, minus B0 looks like this. Okay, our solving for B, it's whatever initially was there. Let's assume you weren't drinking to start with, so there's nothing initially there, and that's 0, and then it's this, okay? And now I need to know how much alcohol am I dealing with. So what happens when 3 beers are consumed all at once, or relatively all at once, close by in time? Okay, so we need now some facts. 1 mole of ethanol, CH3CH2OH, you can figure it out, that's 46 grams. And you can look up the density, and it's 60 milliliters, and that's 2.1 fluid ounces. That's what 1 mole of ethanol looks like. 1 bottle of beer, the normal size of a bottle, they vary, but normal size is 12 fluid ounces, and normal beer is like 6.4%. Yes, there's something called near beer that's much lower, and there's sometimes fortified beer, but no, this is the normal beer, 6.4%, that's ethanol. And working that out, that's about 1.11 moles. So 3 beers is about a mole of ethanol that you put into yourself. Okay? And I'm showing you some equivalents of other things as to what they contain, various spirits and wine and so forth. Okay, now I want to do a time plot of ethanol in human body fluids. I'm taking the initial amount of alcohol in your blood as being 0. I know A0 is 1.11 moles. And remember the volume? It was 40 liters for a typical fluid in you of a typical adult human. So it turns out to be, this is the concentration. That's moles per liter, 0.028. Remember, this is K1, this is K0. That's the time in minutes. At this point, you can work this out. You can graph it. Some of you will graph this in different ways. I happen to use, what's it called? Excel spreadsheet, okay? It's a program, and that's how I put in the numbers to get the graph I'm going to show you, okay? And I did the volume fraction of ethanol in body fluids and the volume percentage of ethanol in the body fluids, and worked this out and made this plot. And here is the percent by volume in your, basically in your bloodstream, okay? And this is the time in minutes. And this is remarkable to me in a number of ways. First of all, it's 100 minutes. This is 20 minutes. It takes about 20 minutes for you to reach the max. That's what I see from the time you start. So it doesn't act immediately. It takes some time. It's on the order of about 20 minutes. Okay? See the value it goes up to? And then look, it's nearly a straight line. Why is it a straight line? Because it's 0th order. Your liver can't turn it over any faster. Okay? That's what's going on. And how many minutes is it? Well, remember 60 minutes to an hour? This is 5 hours to go up to some level like this. Okay, this is hours. This is a really long time. So I begin to understand some things, which you've heard. I'm sure you've heard. Airline pilots are not allowed to drink before they fly the night before. A good thing, right? Because you see how long this effect is. And what else? I enjoy playing chess. Drinking and playing chess at the same time does not improve your chess game. You may think it does during the time you do it, but it does not. Okay, it really is an effect for a long time. Not what you want to do. Okay, I talked about 0.16. What happens if you go higher? What if you take 6 beers all at once? Well, you get then to over 0.30, and it carries the possibility of death from alcohol poisoning. Every year on American campuses, we have people who, for one reason or another, drink so much beer or something all at once and do themselves in. Friends don't let other friends do that, okay? Pay attention to what I'm saying in this. And so that's serious. And we'll go over some more of this. I thought it would be fun to talk to you. See if we started at 7. It's now 7:40. Okay. To talk to you about what it's like among different countries and its effects. It's very interesting because it's not at all uniform. Look, the people who drink the most, this is alcohol consumption in liters per adult, okay? And what do we see? And this is per year, actually. We see that winners are like in Russia, Hungary, Czech Republic, okay? Ukraine, Estonia. They're huge. Compare that to the United States, okay? And then you might say, what about other countries? Now, China has much less. Part of that is that many people in China are missing that enzyme. And so they get no pleasure at all out of drinking, won't drink. Okay, for good reason, too. And then, fascinating, India is not missing that enzyme, but India, Hinduism, and so forth, tends to be against drinking alcohol. Okay, so it's way down. And what countries have the most alcohol problems? Okay, now this is it may be controversial, you don't have to agree with me. One of the worst set of alcohol problems actually exists in India. Yet they're consuming per capita the least. But why is it so bad? It's because they have no tradition of drinking as a social activity. People in India drink to get drunk, okay, if they drink. Whereas in the United States, we have bars, we have we have cocktail parties, we get together. Very different attitude, you see what I'm saying? Quite fascinating. Okay, just want to point it out to you. So many consequences. Let's go on. What about Texas? So what I did is I went to my favorite information source, Google, and I looked up the Texas Department of Transportation, what it says, and it defines the term DWI, driving while intoxicated. First, it tells you that the officer can tell you that you're under DWI when the officer feels like it, without any test at all. That's scary. But that's your law. Okay? But interesting. But then it goes on and says other facts. About every 20 minutes in Texas, someone is hurt or killed in a crash involving alcohol. That's a serious problem. Okay? Quote unquote, in Texas, a person is legally intoxicated and may be arrested and charged with DWI with a 0.08 BAC, blood or breath alcohol. They say concentration. It isn't really concentration. It's the percentage by volume in blood, but they call it concentration. I'm not good at law. That's their term. Okay, so BAC really refers to percent by volume. And now let's look at this, and let's draw in 0.08, which is incidentally the same as California, where I come from. Okay? Look, that's over 200 minutes for our 3 beers. This is amazing. And as to what it does when you can't legally operate a motor vehicle. Okay, maybe in the future we won't have to worry about this because all cars will be driven by themselves. But right now we do. And it matters. Okay, so it's very interesting to see the consequences of this. And now I wanted to go on to a much more difficult topic. Okay, just again by hands. Do you know, any of you know people who suffer from what's called alcoholism? Oh, look at the audience. Many, many, many. Okay, this is real. And this is not rare, unfortunately. And it destroys families. I mean, it's awful, right? And it's actually, as I'll try to make clear to you, it's a disease. It's not a matter of, it can be overcome by willpower, any more than if you have appendicitis, by having a cheery frame of mind, you don't have to worry about having appendicitis. It doesn't work that way. Same thing with alcoholism, I'm sorry to tell you. It isn't simply that, they're weak-willed. That's not the case. What's going on? And what's going on is that new research shows that drinking alcohol leads to the release of what are called endorphins in areas of the brain that produce feelings of pleasure and reward. We really see this. And it goes over, okay, that's true of all people, but why does that mean that some people become alcoholics and others not? Some people's brains rewire themselves in this case. Rewire this so that they must have this feeling, which is sad, okay? We don't, to my knowledge, yet understand fully alcoholism. We know, in part, it's genetic. It can run in families. Okay, that's the facts again. Again, showing something's going on in the biology that way, but we don't fully understand it at all. So endorphins are small proteins with opiate-like effects that are produced naturally in the brain during exercise and during laughing. Dopamine is an endorphin, okay? And people know you get a so-called runner's high from running. People like that, who do that, okay? And laughing makes people generally feel good. Does me, etc. Okay, so we understand this nature. And now alcohol has the same effect of being relaxing and making you feel initially happier, okay? And then I wanted to show you research of 2012. This is interesting. These people happen to be at UC San Francisco, okay? University of California in San Francisco. They did a thing, alcohol consumption induces endogenous opioid release in the human orbitofrontal cortex, I guess that's the front of the head, and something else called the nucleus accumbens, which I don't know much about, okay? And what they do, so this is published, they measured using PET. This is the positron electron tomography. They made a PET scan, okay? Some of you heard about that, to measure the binding of a radio-labeled mu-opioid receptor agonist, this thing, before, notice it's carbon-11, so it's radioactive, not normal carbon-12, before and immediately after alcohol consumption in both heavy drinkers and control subjects. Okay? They took two groups. Drinking alcohol induced opioid release in the parts of the brain implicated in this reward evaluation, which are these two centers. And I have a picture to show you this. This red is where it lights up in their PET scan for heavy drinkers. For heavy drinkers, not for others. Okay? So we're really understanding something about what's going on here in this process. Okay, now the next interesting question from all this is, in any sense, can chemistry, meaning medicines, come to the rescue of what is a very serious problem? I don't yet know how to intervene to stop people who are alcoholics from not being alcoholics in a simple way. As I say, their brain gets rewired. I don't know how to unwire it. But there are some interesting compounds that are given. One of them is called anti-abuse, and it makes the person feel sick or throw up if you drink, and you take this material ahead of time. Another one, okay, can help with cravings, which people have, and a third thing called naltrexone blocks the high you get from drinking. Okay? I thought I'd explain how these work. I hope this will show it. How do these medicines work? What's going on? Because we could learn something from this. Antabuse interferes with this metabolic process. It stops the process with the production of acetaldehyde and prevents the oxidation of acetaldehyde into acetic acid. And because of this, antabuse will cause a buildup of acetaldehyde 5 to 10 times greater than normally occurs when someone drinks alcohol, which again is as if you didn't have that enzyme. Wow, what is it doing? From a chemical viewpoint, it's binding with that enzyme more strongly and shuts it down so it can't work on the alcohol. That's how it works. I hope this lecture, these topics, okay, this is real stuff that I'm talking about, and yet you see it's really grounded in a mix of things. It's a mix of chemistry and biology, and you notice I absolutely needed math to understand what was happening. Okay, there's no escaping that as well, okay, and taking measurements. Physics in this, I mean, many things are going on in this to make this type of work happen. It doesn't belong to just one field, is often the case. It's certainly also about medicine. Okay, and then how does this thing called naloxone work? Any of you hear of naloxone before? One person, several people. Naloxone is what people now wish to have to fight the opioid epidemic in this country in terms of heroin and other things. And if they can get to you fast enough and give you naloxone, they can save you. And I'm going to explain that. So how do these medicines work? Okay, so here we are. Here is alcohol stimulates the release of this beta endorphin, which is like dopamine. Here's this cleft, okay? And there's receptors in here. And this naloxone goes and displaces the opioid. It binds more strongly than the opioid. It shuts down this receptor so it can't see the opioid, okay? Opioids attach the receptors in the brain, but naloxone can knock the opioids off those receptors. This is because it has a stronger affinity to the opioid receptors than do opioids. Once you stop the opioid from being at the receptor, you no longer get the effect of the opioid. That's why the so-called high goes away, okay? So alcohol doesn't do anything for you if you take this. So we have ways, you see, of counteracting some of this. I think I now need to make clear you understand something about me. I am a great fan of alcoholic drinks. I drink, okay? I'm not a teetotaler. I drink. And here I am. I'm actually leaning against a big copper kettle. This is copper vat at the Anchor Steam Brewery in San Francisco. Okay, I've been very interested in drink all along, in one way or another, and maybe this will come up in the questions and answers. I was very fortunate in my own life, and the following happened to me. My own background, religious background, is Jewish, and I went to a so-called Passover service. It started at about a dinner. It started at about 7 p.m., and went to midnight. A little kid. I'm about 4 years old. And to keep me quiet, my mother and father had kept giving me these glasses of sweet red wine, which I thought were delicious because they're sweet and great. And then I noticed somewhere around 11 o'clock or 10 o'clock, I couldn't move my legs. I was paralyzed. They thought it was very funny. I was terrified. And that, in some sense, completely cured me of wanting to go to that state again. That was me, okay, and in a very early age. Just saying. And other people have other experiences, but we tend to be very rigid about alcohol, and in our own society, you know, we've been quite confused. We've had an era of prohibition, and so forth, and we're now going in other directions. We have to be sensible about all this. And I hope you've had fun listening and seeing where all this goes. Now, I'm going to stop this and try, if I can, to show you one more thing, if I can get it. Let's see. So do this. Come on. And try to put this away. And now let's see if I can find some more things. Aha, it went over here. Okay. And get rid of this. And I don't know if this will have it or not. Let me just look. Yeah, this is something I thought would be great fun for you to see. This is a phenomenon. I enjoy all types of things. I think there's science all around us, and I want to just show you one more thing as we close out. It's not due to me, but it's, I think, quite interesting. Let's see if this will play.
Most people who drink wine have seen the weird drops that form around the side of the glass.
Have you?
Traditionally, they're called tears or legs of wine. But what most people don't realize is that if you watch patiently, these drops are actually moving around. They're falling,
That's 12 times the speed.
forming, and refalling over and over and over again. So the obvious question is, what the hell is going on here? First, you have to understand one thing about surface tension. And a neat way to see this is by pouring water onto the surface of a plate and then grinding pepper flakes.
It's very easy to do this experiment. I urge you to do it.
Now, the idea of surface tension is that fluids always pull on other fluids nearby, but the strength of that pull depends on the fluid. So some fluids have high surface tension, others have low surface tension. In our case, we just have water, so the surface tension is the same everywhere.
See?
Each pepper
All
flake
standing still.
feels the pull of surface tension, but feels it equally in every direction, so nothing moves. But if we dip a stick in laundry detergent, which has a lower
piece of
surface
soap will
tension
do
than
this
water,
too.
and then touch the stick to the center
Watch.
of the plate, the pepper runs away. And it runs away because of the difference in surface tension. The higher surface tension water on the edge of the plate pulls harder than the detergent in the center. Okay, but what does this have to do with wine? Well, wine is made up of mostly water and alcohol. And alcohol, like laundry detergent, has a lower surface tension than water. And the other thing about most alcohols is that they evaporate really easily.
Right?
And you know this if you've ever cleaned with rubbing alcohol, where you can see it evaporate off the surface almost immediately.
Right?
Alright, so you swirl some wine onto the side of a glass. And at first you might think this wine would just slip down the sides back in with the rest of the glass. But take a closer look. The alcohol will evaporate the fastest up at the top, where the wine is thinnest. That means that compared to the rest of the wine at the top is actually less alcoholic,
It's
and
evaporating.
therefore has a higher surface tension. And just like with the pepper flakes, this difference in surface tension will actually pull wine up the side of the glass. Now imagine an escalator with a wall at the top, so that the people just start bunching up with no place to go. And eventually, a critical number of people builds up to form a ball, and the ball rolls back down, taking all the people with it. The same thing's going to happen with the wine. Wine is pulled up the side of the glass by the difference in surface tension, but it has nowhere to go, so it bunches up until the drop is big enough that gravity pulls it back down. Of course, with the wine, it's a bit more complicated because it's two-dimensional, but the basic idea is the same. Wine is pulled up through a film so thin you can barely see it. Then, having nowhere to go, it forms a line around the edge of the glass, and instead of one drop, this thickening line forms many drops, much like drops falling from a line of paint on the wall. But unlike the drops of paint, which only fall once, the wine is continuously pulled back up, so the drops form over and over and over again.
Well, I hope you enjoyed that, and I thought it very vividly shows what's going on. There's many other phenomena that are all about us, and so it's a fun topic to look into in more detail in many different ways. And thank you very much for coming out this cold night to join me. I welcome any comments or questions you have. There's microphones here and here, so come on up and we can discuss some more about this if you want.
Hi. I have a question. Okay, so when people get sloppy drunk, like throwing up, gross, is that a buildup of the acetaldehyde similar to what's caused by the disulfiram thing?
I don't know all the details of it, but yes, it is the effect of alcohol on the body. Forgot to tell you, I was so personally disillusioned. First day when I went as a freshman to Harvard, my roommate, who had led a nice sheltered life in New York at some private school, away from home, decided to get and drink alcohol, got drunk, spent the whole night with him throwing up. Not pleasant at all. Don't let people do this. They don't enjoy it, you won't enjoy it either. That's not the point, but it can happen, that's right. Thank you. More questions? Somebody coming? Good. No, that's fine.
Do you know how to cure a hangover?
Do I know how to cure a hangover? No. I don't. I forgot to tell you, though, something else that might, again, that's related to curing things. You might be, you might or might not have seen an episode of Martin, the doctor. I'm trying to think of his last name. Doc Martin, right? Doc Martin, and in which one of the people, unfortunately, takes wood alcohol. So what you need to do, if you take wood alcohol, again, this is interesting chemistry. If you take wood alcohol, what do you think is the medical procedure to try to save you? It's obviously no good for you, as I've explained. First of all, they pump your stomach, but as I explained to you, very rapidly it goes through your stomach into your blood. And you can't pump your blood. What are you going to do? And you can't get a new liver. What they do, believe it or not, is they give you ethanol. They give you regular alcohol. Regular alcohol competes with wood alcohol, with methanol, for the same receptors in your liver. And ethanol binds better than methanol, so it wins. So, and of course, the advantage of this is to then make the buildup over time of the formaldehyde slow enough that your body can get rid of it by various means, and not let it accumulate so much as you get blind in your eyes and such like this. I thought you'd find this interesting. And now you know the basis from this talk of how that works. You come on up forward, please, because everybody can't hear.
You mentioned this genetic predisposition to alcoholism. Is that driven by chemistry, by physiology, neurophysiology, or what is it that's driving
Well, you would imagine for me, everything's chemistry, so including biology, right? So I mean, but it is. It's of course it's genetic in terms of, again, how we're wired. I don't care how we call it. I'm not sure I'm answering quite your question, but it is coming from the fact that those people who suffer from this have a predisposition in their brain presumably from what genes are there that make different proteins, et cetera, so that the effective alcohol is to rewire it that way, so that it becomes a craving.
It's not a simple difference in the K1 constant.
No, it's not. Interestingly, it's not. The question was asked, is it just a matter of difference in K1, the constant, the rates? No, it's not that. It really is very clearly, unfortunately, in many cases, you'll find out that alcoholism unfortunately runs in families. I'm not saying it's the only thing, but it often does. Okay?
Excuse me. Right here?
Please.